Okay, can everyone see my screen okay?
Yes, sir.
All right. So here's the first problem. As I mentioned to, I guess, a few other people who are still in the class, towards the end of the class, you should recognize this problem because we worked in class already. This is the very first amplifier problem that we worked, right down to the very component value. Now, these are C1, C2, and C3 because I actually made this schematic using LT Spice. I believe it's LT Spice. It may have been Electronic Workbench. So I renamed these. I could have made them the right names, but other than that, these values are exactly the same. 4.7K for the RC, 4.7K on for RL, 15 volts, 20 millivolts in for VS. Exactly the same problem. Okay, so here we asked to, and as I've always done with every test I've ever done, I always say, please show your work for full credit. An answer popping up out of nowhere without any supporting work doesn't get too much, if anything. Okay, so I started here with the common emitter amplifier. That's this configuration. I have VA is 120 volts, beta is 150, and your thermal voltage is 26 millivolts. We haven't talked about VA yet. This is called the early voltage. We will talk about it in the Mosfet, and then you'll see why I left it out, because it really doesn't make a whole lot of difference in the operation of your amplifier for the problem we've worked. But when we get to the MOSFET amplifier, we will look at adding VA in, and there's a resistance RO that gets added to our small signal model. Okay. So number one, I asked find a DC bias, which is, so I have these basically set up I'm walking you through it. You have to do the DC bias before you do anything else. So I say find the DC voltage in the current, which means find VB, find VE, find VC, and IE. So let's go here. Okay, so start here with DC bias. We have VB through voltage division is R2 over R1 plus R2 times VCC, comes up to 2.66 volts. Same as the problem we worked in class a few weeks back. VE is VB minus 0.7, so we get 1.96 volts for that. IE is VE over RE, which is 1.31 milliamp. And then IC is approximately equal to IE. If we want to calculate IB, IB is IE over beta, which is about 8.7 microamps. When you're doing the voltage divided bias, you don't need to know what IB is. But since we had beta, I just calculated anyway. So you won't lose any points if you didn't do this. And then we calculated this little RE, which is 1 over GM, which we will need for our small signal operation, a small signal model. So RE is the thermal voltage over IE, which comes out to 19.85 ohms, if I did not make a mistake in the arithmetic. I will make a copy of this and send it to you. So please go back through it also. And if you find any errors, point them out. I have no problem with that. And then we're also going to need this resistor
Is
here.
that R1 plus R2, or is that R1 parallel to R2 for VB?
Oh no, that's plus. That's a little plus there. It's a little tick mark across here.
Okay.
And then we have beta RE is 175 times RE, which is about 3.47K. So we'll need that for our small signal model here. So now we get down to our small signal operation. So we went through this in class. It's not in the textbook, or maybe, no, actually it is. But small signal operation, and I had gone through this in class. Why can we assume that when we have this capacitor across these resistors, there it looks like a short circuit? And I went through that in class a few weeks ago to show that at the frequency at which we were interested, the capacitor's resistance is like really small compared to the resistors. And so when you have, like in this case, XC1, which is your base capacitor, in series with R sub S, this is less than an ohm. And so you can basically show your capacitors are short. XC2 is also, this is your collector capacitor, and it's also, well, the same value capacitor, same frequency, so it's again about 0.15 ohms. Then XC3, which is your emitter capacitor across RE, is even smaller. It's like 10 times smaller, which makes that RE resistor from the small signal model, which normally would be here, looks like just a short. So my C1 would be in here, but it's like 0.15 ohms in series with 1.1 k ohm, which is basically 1.1 k. So we don't worry about that much detail. And then here, excuse me, you would have your C2 capacitor across here. And again, it's 159 ohms in series with 4.7 k. That's 4.7 k. So I put this in here just to remind you why we could basically drop those capacitors out of our small signal model when we're doing looking at small signal operation, because the impedance of it at that point is negligible.
I have two quick questions.
Yes.
It's about IC. Is that IC, is that I beta or IB equal IE over beta?
This is IB equals IE over beta.
Okay. And also, is that milliamperes for that 8.7?
Here,
Yes, sir.
let's see. No, micro.
Microamperes. Okay.
Yeah, 1.31 milliamp, i.e. over 150 gives you 8.7 microamps.
Okay, thank you.
Let's say, feel free to go back and check the math to make sure I didn't hit a button wrong on the calculator. I don't know if it's right, but it's reasonable. I know it should be somewhere in the 10 microamp range. Okay, so we've done our small signal operation, just basically calculating the impedance of our capacitances. I said at 100 kilohertz because I already had an idea that the bandwidth of this circuit is going to be somewhere up in the hundreds of kilohertz. So, excuse me, hundreds of kilohertz, not 100 kilohertz. So we will be within the pass band of our amplifier, or within the desired bandwidth of our amplifier. And that this would basically be what our capacitor value is. If we went even higher in frequency, it would look even smaller. So here's our small signal model. Here's our base collector emitter node here. We have beta RE, GM times VB. This node is VB. Here's my collector node, and from there I have RC in parallel with RL to go to AC ground here. The capacitor across CE makes this a short. So it looks like the emitter terminal goes straight to AC ground. And then on the input here, we have V sub S, which is 20 millivolts peak to peak. It goes through RS, which I didn't write very well, of 1.1 K. Into here we have R1 in parallel with R2, we call RB, large B. And we find a parallel combination of those, and that'll be our RB. Rn would be the resistance looking into this node, which would be this this resistance in parallel with this resistance. So here, Rn is Rb in parallel with beta times Re. And I think I calculated this. Oh, here we go. Rb is R1 in parallel with R2, which was about 9K in parallel with 3.4K for beta Re, which was here. So we end up with about 2.5K for the impedance resistance looking into this node. Our output resistance is the resistance seen looking into the output node here. And that's just RL in parallel with RC. They're both the same value, so the total combination would be basically half of one of them. It's 2.35K. And then we calculate our gain. Our gain is basically this impedance looking my output terminal here, which is RC in parallel with RL, divided by little re with a negative sign because the output is 180 degrees out of phase with the input. And we get about 118 volts per volt with 180 degrees phase shift. And so then I got down here, starting to run out of space. But what we asked for was, what was the output voltage? We know what the gain is, but we have to find out what the actual input voltage is here as a function of my source voltage here, which is 20 millivolts. So that's why we calculate our input impedance, because if I have a voltage source here, a series resistance source resistance here, into this resistance node here, I basically have voltage division. So then my Vn will be Vs times Rn over Rn plus Rs. This gets a little small, but that's 20 millivolts times 2.5K over 8.6K, which turns out to be 13.9 millivolts. So I have 20 millivolts for my source. The amount that actually gets to the input here through this voltage division is about 4.
For the game, would it have been okay if we had defined that formula as RL prime?
That's fine. I don't care what you call
Okay,
it.
cool.
Yeah, the author uses RL prime. I have a tendency not to, because I like to always be aware of exactly what's involved in my calculation. And he does RL prime because, you know, he doesn't have to type as much. You just say RL prime is RC in parallel with RL, and use RL prime from that point on. I don't care what you call it. So here's Vn is 13.9 millivolts. My gain is a magnitude of 118 volts. So then my output is my gain times my input, which is minus 118 times 13.9 millivolts. So your output voltage, and again, this should have the magnitude of it, is 1.6 volts, where the input was, or the source generator input was 20 millivolts. I get 1.6 volts peak to peak out. So that gets us input impedance, output impedance, and it gives us our gain. Now we look at frequency response. So here's our small signal model, or it is your small signal model showing the your capacitors. And so now, in order to find our poles, our low frequency poles are going to be due to our C1, our C2, and our C3 capacitors. Okay. And the approach to doing this is, you have multiple active elements in a circuit, like these capacitors here. What you do is, to find the pole associated with this capacitor, is that you set all the others to 0, other capacitor values to 0. You leave this one in, and you find a Thevenin equivalent resistance seen by this guy here. So we'll start here with FLB, which is this C1 capacitor. And the impedance seen by it is RB plus RS. Here. Oh, excuse me. Not RB, RN plus RS. So RN is this in parallel with this, which is 3.6K. And this is 10 microfarads, which gives me a pole frequency of 4.4 hertz. And then we look at our low frequency pole due to capacitor at the collector. And the Thevenin equivalent resistance seen across this terminal here, or the resistance across this terminal, is RC plus RL times C3, which gives us a pole location of 1.69 hertz. And then the last guy here, the low frequency pole due to the emitter capacitor, is 1/2 pi R Thevenin as seen by CE. And see, where did I put it? Equivalent resistance seen by CE is going to be RE in parallel with beta RE plus RB in parallel RS, and all of that divided by beta. And so I'm trying to think, where did I don't think I showed the equation. Let me slide this up a little bit. Oh, here it is. So the resistance is, this is RE, which is beta RE divided by beta, plus RB in parallel with RS divided by beta. So we calculate that, and we get 26.39, excuse me, 26.39 ohms. And I'm wondering if I missed something here. Probably something I didn't write that I want to write. But anyway, so the frequency due to your emitter capacitor here is, we plug the numbers in, it's 60.35 hertz. So this is the highest frequency pole of the low frequency poles, which makes this F sub L the dominant low frequency pole. So F sub L, the dominant low frequency pole, is F sub LE, which is about 60 hertz. Now we want to look at your poles due to your high frequency. And these poles are due to your internal capacitances. So there's a capacitor across here, C sub BC, and there's a capacitor across here, C sub BE. And so I've already shown where we use the Miller's theorem to replace this capacitor here with its equivalent on the input side here, and on the output, C Miller out, C Miller in. So now C Miller in is C sub BC, which was given, times 1 minus the gain. So that's 4 picofarads times 119 is 476 picofarads. And so the total capacitance here on the input is C Miller in plus C Miller in parallel with CBE, which is C Miller in plus CBC. So they add, when they're in parallel, you get 480 picofarads for this parallel combination here. On the output side here, all you have is C Miller out. And C Miller out then was just C, so CB times 1 minus 1 over the gain. Well, the gain is 100, almost 120. 1 over that is going to be negligible. So you basically C Miller out is CBE, which is about 4 picofarads. That's this guy here. So having my capacitances, now I need to find the equivalent impedances seen by them. Next page. So F sub H by high frequency pole, due to the output capacitor C out, is 1 over 2 pi R Thevenin as seen by C out times C out. So R Thevenin seen by C out is basically RC in parallel with RL, 2.35 K. And so I plug that in here. C out was 4 picofarads, and I get 16.9 megahertz for that pole location. And wait a minute. Oh, okay, come on. Forgive me. What I'm seeing on the screen and what I'm showing is a little different. So actually that was the frequency due to C out. The frequency due to your input capacitance C in is R Thevenin seen by C in, which in this case is RS in parallel with RN. So it is with 783 ohms if my calculation is correct. And so plugging that into here, I get your high frequency pole due to your input capacitance CI is 434 kilohertz. So here are our two poles. This one is lower in frequency. So my high frequency dominant pole is F sub HI, 434 kilohertz. And I think the last thing we asked for, and it didn't have to be very pretty, it just had to be representative because this is not to scale, was a Bodie plot. So I take my 118 volts per volt for my gain, take the log of it, multiply by 20, and I get about 41.43 dB. So I have to plot on my Bodie plot. This is in dB, your gain. And of course, this is in log frequency. So this is scales of 10, but I did not give you log paper, so anything reasonable would be accepted. But the most important parts of this are F sub L and F sub H. F sub L is about 60 hertz. F sub H is about 434 kilohertz. So this is our bandwidth. F sub H minus F sub L is the definition of bandwidth. Okay. So at F sub H, my gain is actually down 3 dB from this point here. So it's about 38 dB here. And at F sub L is also down 3 dB, so it's about 38 millivolts here. Excuse me, 38 dB here. So I just drew this dotted line across here. And so here's F sub L, here's F sub H. So the slope of this, though, is from F sub L until it encounters the next pole is basically 20 dB per decade of frequency until it encounters this next pole, which gives another 20 dB per decade, which means the slope is now minus 40 dB per decade. And when it encounters this last pole here, it adds another minus 20 dB per decade to the slope. So this slope here is minus 60 dB per decade. And here on the upper end, from F sub H up to F sub out, FH out, you're at 20 dB per decade. And when you encounter this other pole location, it adds another 20 dB per decade on the high end. So this is minus 40 dB per decade, which I didn't label on here. Nope, I'm going to have to take points off of my key. So this will be minus 40 dB per decade. And again, the bandwidth is F sub H minus F sub L. In this case, it's 434 minus about 60 hertz, or basically 434 kilohertz is the bandwidth of this amplifier, with a gain of about 41 dB, or about, well, we can just say it's 120. So that's pretty close.
I got a question.
Yes.
So points from your key go to everybody else's test, like it'd be negative from the key and plus to everybody else's test?
No. Nice try though, but no. But you know what? That's not true. I think I'll take a point off of this right here. That's probably what I'll take off of your test if you didn't get it right. I'll take this 1 point off and I'll give it back to everybody. How about that?
That sounds good.
I'll take the 1 point divided by the number of people in class though. And that's of course your number.
Oh, we don't have to divide it.
We
Yeah.
can divide it as long as we multiply it by the number of people in the class first.
And then divide again by the number of people in class.
No, just divide once after we multiply it.
Okay.
And then we multiply by the entire student population, and then we got a good score right there.
Multiply by beta. And, yeah.
Okay. All right, we can do that. No, I think, you know what? I think I like alpha better. We won't do beta, we'll do alpha. Alpha is, of course, beta over beta plus 1. Which is about 1. Actually, slightly less. We'll call it 0.99. So, that was the exam. And so I heard rumors, because you know how students talk. A lot of them just lying. You know, in one of my classes, they were lying. They were saying, y'all talking about how hard the test was. I said, it couldn't have been that hard. It's the same problem I gave them a few weeks ago that we worked in class. And I know they paid attention in class. And I know that they worked the example problems that I gave them. That was in the book. and have them turn it in. So if they did all of that, this would have been a piece of cake. And that's how I want to believe it is until I look at your exams and you prove me otherwise. Any questions? Now,
Can we actually, like, are you gonna ever give back what we actually made on the homework?
yep, you can get all that stuff back.
Okay.
Now, the whole purpose of the homework, though, was for you to practice. So you got this. Yeah, that's the whole purpose of the homework. That's why I gave you those particular problems, because they all look exactly the same and they all work exactly the same. I threw a couple of things in here that's not in the book, like this impedance here, but I showed you that. That shouldn't have been anything that freaks you out. Everything else is straight out of the book and straight out of the homework. The purpose of the homework is just like going to practice, whether you play an instrument or you play a sport. The homework is practice. You don't show up at the game, you don't show up at the performance having not practiced and then be surprised, hey, that didn't go very well. It's like, no, really? I wonder how that happened. I had one student who was my class a few years ago. He ran track. He was in my digitalology class. He wasn't doing well. And so I was talking to him. I said, oh, so you ran track? He said, yeah, I run track. I said, oh, what's your event? He told me where's the event. Well, I said, okay, well, that's cool. I said, go back to this class. How often do you practice? I mean, how often do you study for your class? He said, oh, about 3 times a week. Oh, okay. So the 2 times we come to class is probably what he was considering studying. And some other time, I said, okay, wow. I said, so you're on the track team, you run this event. How often do y'all study? How often do y'all practice? He said, oh, we practice every day. I said, really? Why is that? And you can see the look on his face, like, so I don't look like a damn fool when I get out there to meet. It's like, yeah, that's what the homework is for. It's for practice. Anyway, that's exam number 1. Last time I taught this class, there were actually 2 problems. So this is actually watered down from the last time I taught it. What you will get coming up next will be the rest of what was on the exam the first time I taught it. So let me see if I can switch over here. I think someone asked me how many tests you get to drop or do a drop test. Don't count on those. What I used to do when I was asked that was, if you can tell me how I can get the time back from making the test and how I can get my time back, my lecture time back from letting you take the test, and how I get my time back from staying up tonight and grading this test, and get my time back from going over the solution. If you tell me how I get all that time and effort back, then we can drop the test.
I got one. Hire me as a TA.
What's that?
Hire me as a TA.
No, you don't get it back. So I'll let the department do that. You know, I'm actually I like doing my own grading. Yep. Not because I like being mean, well, although I do kind of get off on that too. Nah, I'm looking for certain things. When I teach, I'm actually looking for certain things. And what I don't let students get by with is just enough, thinking they can get enough partial credit to pass the class. If you can't show me by the end of this class that you can walk through this problem and work the majority of it, there's a really good chance you're not going to pass this class. And that would be unfortunate because there are no secrets. I'm teaching you exactly what I'm going to test you on. No secrets. So the only other variable there is, are you preparing? Or are you showing up at the meet with flip-flops on, or I guess y'all don't wear flip-flops these days. I guess they're Crocs now. Showing up with some Crocs on, thinking you're going to run a 200 meter. Okay, we'll see how that works. So this is where we're supposed to start the class, frequency response of small signal amplifier. So this is a Mosfet amplifier. Mosfet stands for metal oxide semiconductor. field effect transistor. So it operates a little different than a bipolar transistor in that there is no current flowing into the gate here. This right here is basically a capacitance. And so the way the MOSFET works is you put enough voltage or charge on this gate right here that actually allows you to have conduction through this part of the circuit here, which is called the channel. So the terminals are the drain, gate, and the source. But we do use a voltage divider bias to generate VG. Okay. Now the current that flows through this guy is called a square law device because the current that flows here is proportional to the square of the gate to source voltage. So we got a second order equation we have to solve in order to get our operating points. So let's see here, which again, we are not going to go through in this class. I will give you, like in this example right here, it tells you what the gate to source voltage ID R, and from that you can calculate GM, and RO and RM is 1 over GM. You'll be given this. We're not gonna spend class time doing solving second order equations. That should have been covered in electronics 1, but if it hasn't, you can go back and look it up. Yes.
So you said that by putting voltage on D, it allows it to like basically switch on, right?
Nope. By I think you said D, by putting voltage on G.
Okay.
Yeah. Right here, this voltage comes from this VDD through this voltage divider. So the voltage VG is 1.2 meg over 1.2 plus 2. So it's about, what's that? 1 over 3.2, so about a third. So about 6 volts is what VG is.
Okay. Another thing is VD basically just another way of saying VCC, just saying the voltage that's coming into the circuit, like, or is there actually a different thing?
No, this
VDD.
Oh, VDD.
Yeah.
VDD. Good question. VDD is a supply voltage. They typically use VCC for bipolar transistors and use VDD for MOSFET transistors for some reason. And it's been like that forever and a day. I don't know why they use different nomenclatures for the supply voltage. It doesn't matter what you call it; it's a supply. But you're right. In for MOSFET circuits, they usually use VDD for the supply voltage. Right. Over here we have IRF610. That is this MOSFET transistor. It has some K, which is 100 milliamps per volt squared, and your threshold voltage is 3 volts. What that means is you have to have your gate voltage at least 3 volts higher than your source voltage in order for this device to start turning on. Remember when we had the bipolar transistor? This was like 0.7 volts higher. Well, this can be even more than that, but it has to be at least 3 volts higher than your source in order for you to get current flowing from your drain to your source. So this is the IRF610. There are other MOSFET devices. I think the 820, IRF 820. They have a different value of K prime. So
would that 3 volts change with like every different model, or is that just constant like that 0.7?
No, it will change from transistor to transistor. That's another good question. With the bipolar transistor, it's always a diode junction. This is always this is basically a capacitance, but it depends upon some basically chemistry. Let's see. I think everyone, I don't know, has everyone had semiconductor devices?
No, sir. We're trying to find somebody to teach that.
Oh crap. Tell Dr. Jackson to give me a call. I was the first one to teach semiconductor devices, by the way.
All right.
Yeah, it was interesting. I was talking to Dr. Mansour last fall about that, and he's like, "Yeah, he's someone to teach semiconductor devices." And I just sort of laughed. I said, "You don't remember, do you?" It's like, I said, "I was the first one to teach semiconductor devices back in 2010. The first cohort of electrical engineering students that come through, I taught them electronics too. I taught them circuits too. I taught them semiconductor devices." So, okay. Yeah, I'll mention it to Dr. Jackson. If I remember, maybe I'll send her an email too to see if we can work something out. But yeah, I taught that. I think I taught the first two classes of semiconductor devices I taught. Okay, so we have our gate to source voltage. So right here it says applying the analysis procedure of chapters 8 and 9. That's where we actually covered the DC operating point. You actually get your gate to source voltage is this, your drain current is this, your transconductance is this, your RO, which is this VA here. What was it? VA over your ID gives you this value here, RO. I said we'll talk about that a little bit more when we get into the small signal model for this. And you can see why we can put it in or we can ignore it. It usually doesn't make a whole lot of difference. It depends on what you have connected here at this node here. So here's our circuit. So now we, just like we did with the bipolar, let's calculate our Rn because we need Rn because this is what we consider the input to the amplifier, or the other side of this capacitor here. And this signal source here has a source resistance associated with it. So all of this 50 millivolts is not going to show up here and get amplified. So when we calculate our input impedance, we can do the voltage division between the input impedance and R and calculate how much of this 50 millivolts actually shows up here at this node and get amplified. When we got that, then we can calculate what our V out is. We can always calculate the gain without knowing any of this, because the gain is just the ratio of this voltage to this voltage, which we can calculate even if we don't have an input connected. We can calculate. So when we say the gain of the amplifier, we mean the gain of this circuit here minus this stuff here. This is just a signal source. And we can also calculate the gain including or not including your load resistor here, because your load resistor may change. As you change your load resistor, you'll actually change the gain of this amplifier. Because remember, just in the bipolar case, I can look at this and sort of tell you what the gain is going to be. It's going to be your GM times RD in parallel with RL. If I change RL, then my gain changes. But I'm kind of jumping ahead. But so let's go back down here. So we calculate our input impedance, Rn, which is what we call RG because it's connected to the gate, which is R1 in parallel with R2. So it's 2 megohms in parallel with 1.2 megohms or 750 k-ohm. So that's the impedance looking into this node. Then the output impedance is the impedance seen looking into this node, which in this case, actually, I'm sorry, looking into, output impedance does not include the load, I'm sorry. Looking into this node, you're going to see RD in parallel with little RO, which is about 2.8K. And let me shift over for a second to show you the small signal model.
Dr. Biz, is there any specific reason on this MOS amplifier that the resistances are so high, or is that just they just pick, higher resistors?
They are high because you don't need a lot of current. What we did not do, hey, you know what? That's a good question. There's a lot of stuff we can cover in just as basic stuff we've done before from a practical point of view. We hadn't really talked about it. So you ask yourself, how much current does this amplifier here draw from the power supply? Well, from here we get what? ID. What flows in here, flows down here. From a DC point of view, we get ID. Okay, which is 2.4 milliamp. And we also have from our supply current flowing through here. This is a MOSFET, so there's no DC gate current flowing here. And this is a capacitor. There's no DC current flowing through there. So all the current that flows from this 18 volts flows through here to ground. And so that would be 18 volts divided by, I think I just talked about that a minute ago, 3.2 megohms. So it's going to be like microamps, 6 microamps. So we got about 6 microamps here. And what was it? 2.4 milliamps here. I can make these instead of 2 megohms. I can make this a 2K and a 1.2K. So now what I've done is made this from microamps to milliamps. So if this was a 2K and this is 1.2K, so that totals about 3 milliamps. 18 divided by 3 is 6. But there will be 6 milliamps flowing just through these resistors right here, doing nothing other than generating a voltage here. Well, I can generate a voltage here without drawing that much current by using bigger resistors. The other reason you want to use a larger resistor here is the more current you flow, the hotter your circuit's going to get. So depending upon where this thing might be located, it might be in a place where it can't get any cooling. And so you got all that extra current that's just running through those resistors for no purpose other than we just got small resistors. Okay. But that's basically why they're so large. But that's a good question.
So basically for heat reasons, and also it makes it easier for it to flow in the other parts because it's going to be like plus 3 volts whatever at that point, right?
Well, not so much easier to flow in the other part. You don't want to pull any extra current off of your supply voltage for no good reason. What if we, instead of running this off of a supply voltage of 18 volts, it was a battery? The smaller I make these, the more current flows out of this battery, the quicker the battery dies. So if I'm designing this thing to be out in the field somewhere, not connected to power supply, just running off of batteries, I would want those resistors to be larger because they'll draw the least amount of current from my battery could last longer. Now, you're right. There are probably other things running off of this 18 volts too. This is just a little amplifier we're looking at. This is not whatever the complete design is. There'll probably be a lot of other these amplifiers and other signals coming in. This is just one amplifier amplifying one signal. If you have other sensors, you have an amplifier for each one of those also. So every one of those will be drawing current. And if they're running off of a battery, the less current less what's called static current that you can draw, the better your battery lasts longer. So you don't have to replace it as often. Even if you're running it off of something like batteries that are charged up by solar cells. I did some consulting once for this company up in near Traverse City, Michigan, which is the upper part of the Lower Peninsula of Michigan. And they had natural gas wells that they were monitoring how much gas was being pumped out of these wells. And there was no power out there. They had solar panels and they had a battery pack. And so the solar panel would charge up and keep the batteries running. But one of the problems they ran into was, well, this is northern Michigan. And if you've ever been in northern Michigan in the wintertime, there's a lot of snow. So the solar panels could get covered with snow. And so they can't see the sun. And as they're getting more and more snow, your batteries don't recharge now. So we had to come up with a way to, how do I maximize the amount of time my system can run if my solar panels are now covered with snow? And one way that I suggested to them was, let's turn our electronics off. And we will turn them on periodically when we need to do a reading. And this was also what's called a SCADA system, supervisor control and data acquisition. So there was a radio link to the box that was monitoring these wells. Well, you didn't want to be constantly talking to the box, so we set it up so that I think it was like I believe it was every 10 seconds or 20 seconds, the circuit will wake up and it will listen to see if anyone's trying to talk to it from an RF point of view. And the answer was no, then it'll go back to sleep. And it'll wake up, maybe, I can't remember how long it was. Maybe like 20, 30 seconds later to see, is anyone trying to talk to me? If it is, then you power up the rest of the circuit, you transmit the data they're trying to collect, and then you go back to sleep. So you can either make these larger to draw less static current, but there are also other ways of just like turning your circuits on and off periodically when they're not doing anything. Your cell phone is a perfect example of that. While you got, I mean, I put my phone on the charger every night when I go to bed, but I'm usually at about, I don't know, 60% when I hook it up and just let it go ahead and top off at night. But you could be in standby mode for days and not die. Well, the way it does that is it has sensors. And one of them is it's sensing, hey, is anyone touching my screen? No, then I don't need to turn the screen off because the screen draws a lot of current. So little things like that, little practical things is how you can solve problems of, I don't need more power. I need to conserve the power I have, so I won't be burning things unnecessarily. If I'm not talking on my phone, then the power amplifier is off. That's another big energy sink for modular or mobile devices like this is transmitting your signal back to the cell tower. But if you don't need to talk to the cell tower very often, then you don't do that, and you save yourself a lot of power and your battery lasts longer. Okay, so that was a long-winded version of why are these resistors so big. They help consume power by having very little current flowing through here, but I can still generate the voltage I need here. I can scale these. I mean, I can make this a 12 meg and a 20 meg ohm resistor, or I can make it 10 times as small, and you'll get more current. So the value of these was chosen so that the amount of current that flows through here is minimal compared to the current that's flowing through here. All right, where are we going with this? Oh, I want to take a quick look at you. I've been talking about the small signal model. Let's take a look at it, and then we get back to the calculations. So here is the small signal model for your Mosfet transistor. You have a GM times VGS, where VGS is the voltage here between your gate and your source. You notice there's no resistor here because there's no diode junction here. This is a capacitor, basically. So you don't have any DC current flowing through here. This RO, every amplifier has an equivalent output impedance. This is R low O for AC output impedance. And its value is given by VA, the early voltage, divided by my drain current. And I think in this case, we calculate that to be about 50 kilohertz. Kilohertz, my goodness. 50 K ohms. So, but we'll get back to this in a second. Oh, here it is. Let's talk about it real quick. RD, which is 3K, in parallel with 50K, it's going to be pretty close to 3K. So this is so much larger than these. We can actually, after we do a couple of calculations, we'll see this guy right here can usually be neglected, and it won't have a large effect on the accuracy of the output. Okay. So that's why I started to mention in the bipolar case, it's like, nah, we'll talk about it when we get to the next transistor. And then just as we can calculate the impedance of these capacitors and show, hey, this guy's actually shorted, we can also compute the value of this resistance and see this is so large compared to the rest of these resistor values that we can pretty much ignore it and just don't even draw it in the circuit. Okay, so here's my small signal model for the Mosfet. The rest of it is just like the bipolar. My drain terminal here is like the collector. Here's RD to ground.
So So do you still want us to draw it when we actually like get on the test or homework to still draw RO?
Yes.
Okay.
If you VA draw it and do the calculations. And then on the exam, I'll tell you whether or not you can ignore it or not.
Okay.
But yes, you should. I want you to be aware that it's there, even if we decide most of the time we can neglect it. You don't want to pretend that it doesn't exist. It does exist, but we make the choice to ignore it because it's so much larger than the other resistors. So as with all things in engineering, you have to have an understanding of what you can ignore and what you can't. You know, this is 50K, but what if I had this was a 50K resistor here, and now if I have a 50K resistor here and a 50K resistor here, and I ignore this one, then its equivalent resistance is twice the size it actually is. RD in parallel with RO. If RD was 50K and RO was 50K, the parallel combination is 25K. But if this is 50K, RO is 50K, and this was 3K, parallel combination, oh, here it is, it's about 2.8K. So it's approximately equal to 3K. So we don't have a whole lot of error here. But the closer these two get to being in value, the larger the error you would get when you try to neglect it. Okay. So this 50K is more than 10 times bigger than this 3K. All right. And then here out the gate, we have R1 in parallel R2. That gives me RG. And here's my signal source, my source resistance, my coupling capacitor C sub G. Here I have a bypass capacitor C sub S, and my coupling capacitor C sub D that couples my load to my drain. Remember, if I did not have this here and I cooked this RL directly to here, it would change the amount of current that's flowing out of my drain. It will change my operating point. Again, that's why we have this capacitor here in series with the load, this capacitor here in series with the signal source, so that we don't mess up our DC operating point that we've worked so meticulously hard to get. And this guy right here, well, he just bypasses this from an AC point of view. DC, he does nothing. He just opens circuit. Okay, so if we go back over here, RO, we have RL prime, which is RO in parallel with RD in parallel with RL. Very similar to, I'm sorry. So the output impedance, looking through my drain node here is what? This in parallel with this, parallel with this guy right here. Remember, this right here is basically a short. So RO in parallel with RD in parallel with RL. And I don't, well, let me mention this. I'll send you this. This is not included in the material I sent you before. So we have RN, we have RO, we have RL prime. And so our gain then is V out over VN, which is GM over RL prime. What's RL prime? RO, RD, and RL. And so remember, GM is a little over, one over, in this case, it's not RE, it's called RM. But my transconductance times my resistance seen looking out of this terminal here, including the RO that's in here, gives me a gain of about minus 73. And let's see, what is this? So here's my gain here. So this is the gain from this node to the output here. But what is the gain from here, this signal, to the output? Well, that's GM as RL, but we have this voltage divider of RN over RN plus, this should be a S, and the S is missing, a source. So this right here is a fraction that will decrease our total gain a little bit. But in this case, not much at all. It's like, well, why not? Well, our voltage divider here, Rn over Rn plus Rs, these guys right here are huge compared to this. That's the other reason you want to use large resistors here, is that you have a large input resistance, okay, 750K compared to 1K. So then our gain from here to the output, or from here to the output, that's pretty close to the same. Minus 72.6 to minus 71.6. So this right here, you're like 98, almost 99% of the signal, of this signal actually gets to the gate here to get amplified. So that's our small signal, our RN, our R out, and our gain so far. Any question before we get started? Actually, probably stop for about 5 minutes, let me cool my heels, get something to drink, and then we'll come back and we'll go through the frequency analysis. Any questions so far? Okay. So here we have, we'll talk about it real quick, low frequency analysis. So the general low frequency model for the amplifier is presented here. Okay, so how do I know it's low frequency? Because all the capacitors are still in the circuit. And so I'm going to need to find R Thevenin as seen by each one of these in order to calculate the pole associated with each of these capacitors. That'll be my low frequency. Remember, the low frequency model, low frequency poles are always associated with the external components that we put here, here, here. The high frequency pole is associated with internal capacitances inside of your device here. All right. And it is 7:39. I'm going to pause recording here, take a 5-minute break, and then we'll come back and finish the rest of it. Okay, so here's our small signal low frequency model, and later on we're going to have a small signal high frequency model. So here we have the cutoff frequency introduced by your coupling capacitor C sub C, and that's 1 over 2 pi. So the resistance seen between the terminals of this C sub C here, I'm sorry, C sub G, is R plus RG here. There's no conducting path here. And so plugging in the numbers, we get a pole associated with this capacitor of 0.2 hertz. That's about as close to 0 as you're going to get. Now here, a cutoff frequency introduced by the coupling capacitor here, C sub D, which couples my load resistance RL to my output, or my drain here. This is actually output, where I take the output from, but this is how it couples to your drains.
I got a question over there by G to the right. What does that say? Is that VGS?
Right.
No, to the right. The little gap
Right here.
right there. Yes.
Yes, that's VGS. This is G. This is your S terminal. So this is VGS.
Okay.
Okay. Let's see. Say help. Let's zoom in a little. Okay, so back to my drain capacitor. So it is CD times the equivalent resistance seen between its two terminals. And it sees what? It sees RD in parallel with RO. Remember, this is short. So RO goes to ground, connects back to here, and RL. And so it gives me a pole location of 2.5 hertz. And then we have this other guy here. Here, sorry. Cutoff frequency introduced by the source bypass capacitor C sub S. And that's R Thevenin seen by C sub S is going to be RS in parallel with RM, which is 1 over GM. This is just like our little RE from bipolar. And so it's 1.5K in parallel with 30 ohms, or about 30 ohms. And so plugging the numbers in, we get F sub L due to your source capacitor of 54.1 hertz. This is the highest frequency of the low frequency poles. So this is my dominant low frequency pole. Let me zoom out a little bit. There we go. We also have zeros here, which we are not going to talk about in this class, but zeros are actually good. Poles cause your gain to decrease. Zeros actually cause your gain to possibly increase, or at least not decrease. But we're concerned about the zeros at this point, excuse me, the poles at this point. But if you had signals and systems or controls, you probably talked about poles and zeros. Okay, now high frequency analysis. So here is our simplified Miller's equivalent high frequency model. Yeah, there was something missing here, I thought. They had C sub between the gate to drain here. And then we're using Miller's theorem. This disappears and you get a capacitor here, and you have a capacitor here, which I think this doesn't need to be here anymore. So, oh, sorry, here we go. So the data sheets for the IR6010 list the following as typical internal capacitances. So it's called CISS, in this case, 140 picofarads, and C out SS of 53 picofarads, and CRSS of 15 picofarads. So what do we do with this? So the inter-electrode capacitances, and I wish we had signals, semiconductor devices, because this will make a little more sense. Inter-electrode capacitance are determined from the following data. So this you get from the data sheet, and from that you can calculate our CGS, which is CISS minus CRSS, which is 125 picofarads. That'll be your capacitance across here, your gate to source. Your gate to drain capacitance, which would normally be across here, is CRSS, which is 15 picofarads. And our drain to source capacitance, drain to source across here, is C out SS, COSS minus CRSS with 38 picofarads. So you'll be given this stuff. You don't have to remember. You don't have to memorize it. And I won't give you a data sheet and make you look it up. So it says a simplified high frequency model amplifier, including Miller equivalent capacitors, are shown below. So we've already taken this and this and this. And if you ignore these little scribblings I put in here, you basically end up with C in and C out, where it combines all these CGS with to get CI in here. And let's see, one last page. So I will send you this. You don't have it. So here we go. Miller equivalent capacitance, C Miller in and C Miller out. And the overall input output capacitance is C in and C out are determined from the equations. 964, 967. So C Miller in is what? It's the gate to drain voltage. gate to drain capacitance. That's times 1 minus the gain being negative. So we'll have C Miller in look like the gain times CGD. So it looks like 1100 picofarads. And C Miller out is the gain. That's the gain. I'm sorry. Gate to drain capacitance times 1 minus 1 over the gain. In this case, it will be about 15 picofarads. And so C, and then all the capacitance on the input is C Miller in plus CGS. This is 1229 picofarads. And the output, all the total capacitance on the output is C Miller out plus C drain to source, which is 53 picofarads. So now we have 2 more poles to calculate. F high on the input is 1 over 2 pi RG in parallel with R times C, which is 12.5 kilohertz. And then the cutoff frequency introduced by the output capacitance C out is 1 over RO, RD, RL. And this is looking from your drain capacitance or your output capacitance, which is 1.36 megahertz. So what can I say about this amplifier? Well, its dominant high frequency pole is at 12.5 kilohertz. Not a whole lot of bandwidth. And part of it is this capacitance here is so large. But also, RG, let's see, this is RG in parallel with R. That's about 1K. So RG didn't really have a problem here. It's just that we have so much capacitance for this particular transistor that we don't get a whole lot of gain out of it. Excuse me, we don't get a whole lot of bandwidth out of it. We got an okay amount of gain, but we can't go too high in frequency before the gain starts to roll off here. Okay. And as in the last exam, here's the summary of the equations for the frequency response analysis for the common source amplifier. So here are all the equations. You'll just have to plug the numbers in. So there's low frequency analysis, high frequency analysis. Any problem I give you an exam will have, I would have given you the, I would have given you the DC operating point rather than have you calculate that. That's just, you can do it, but it's just math. And there are more important things to cover right now. So that is the other type of problem that would have gone on the exam. And you will see it. Let's see. When is spring break?
I believe it was the first week of March. That's what I found when I looked up online.
Okay, because I've been having a problem finding stuff online. So when is midterm?
I heard that was the third week of March.
Okay, I'll look it up. So midterm and spring break. Wait a minute, third week of March, we come back. So we've gone January, February, take a break, midterm. Yeah, that's about right. Because we actually started a week earlier than we normally start in January. So everything's been pushed up a week. Okay. Well, so we need to cover this material here. And then we'll move on to some of the other material in this class. We're going to do operational amplifiers. So these right here, these are what's called signal transistor amplifiers. I got some small little signal, here. I can put together amplifier with a gain of 100, and so they'll boost the signal up. But there are other applications where this just doesn't quite cut it. And so we're going to look at some other amplifier. It's called op amps or operational amplifiers. And those amplifiers actually have 2 input terminals, and they're capable of doing mathematical operations, which is why they're called operational amplifiers. And we will look at a lot of those. We'll look at the amplifier, the gain stage. We'll look at it. We can use it as a calculate the logarithms. We can do addition. We can do subtraction. So we can actually do mathematical operations with op amps. Before there were digital computers, this is how it was done. Okay. So I know everyone's going Google Gaga over digital computers. What do we do before digital computers? Well, we didn't use an abacus. We used analog computers. And they did a pretty good job of getting us to the moon and back. So we will look at some of that. I actually used an analog computer once when I was undergrad at Auburn for our control systems. You basically just plugged up the different functions through jumpers to get the function that you want to implement. Okay. That's all I have for now. So first of all, let me stop recording because the more I record, the bigger the file gets.